Alright, we are going to be going over how to traverse a binary search tree. So we're going to start by just reading a function that we're calling mystery, and we're going to work through the mystery function to see what it does. We're going to assume that the root is passed into the mystery function, meaning that cur is pointing at the root node of this example tree. So we're going to start this off this way, just read through the function and see what we get. I have to warn you that tracing recursive functions is really confusing, and so doing this in class is fun because we get to kind of do it together and check in, and you get to say, oh yeah, the next one is 47. But you need to follow along, and if you get distracted at any point while we're tracing it, it's going to be hard to come back. So make sure you're ready to do this with me. Once you do it a couple times, it becomes really easy to read the function, but it is a little bit overwhelming at first. So let's give it a try. So cur starts out pointing at the 55 node. Since it's not null, it's going to go down here to recurse on the left node. So basically the left node gets passed into the function, and so now we have cur pointing to 48. Same thing happens again, basically. We are inside of 48, it's not null, so it passes its left node into the function, so now cur is pointing to 47. It does it one more time. We're now in 47. 47 passes its left node in, which is a null pointer. So now we have cur pointing here. As you can see, when we're inside of the cur's recursive call to mystery, and it's a null pointer, it's just going to return out right away. And so we go back up one, and we just went left, and now we're here. So it's going to print out 47. And so we've gone left, we've printed out 47, and now we're going to go right. Well, the 47's right node is just a null pointer, so the same thing happens again. It's going to go into the recursive call and then come right back out again. And so then we've basically finished finally one full recursive call to mystery on the 47 node. So we went left, we printed, we went right, and now we're done. So we're right here. So we're going to go back up to 48, its parent node. Okay, so now we're at 48. Where are we in 48? You have to come back and think about it for a minute. So we just went left and we finished that. So now we're going to print out 48. Finished that, and now we have to go right. So going right means we're going to go to 50. And when we go to 50, we're in a whole new call to the mystery function for 50, right? We've just entered it for the first time. So we're going to go left, which is null pointer, so it'll come right back out, and then it will print. And now it's going to go right. So we went left, we printed, and now we're going right inside of 50. So now we're at 54. We're in a whole new recursive call function to 54. This is the first time going in. And so it's going to go left, which is a null pointer. It's going to print, which is 54. It's going to go right, which is a null pointer, so it'll come right back out. And now we've finished the recursive call to mystery for the 54 node. So that goes back up, and it goes to 50. So now cur is 50. But remember that we've already finished 52, right? We just came out of 50's right, so we're going to go back up. And now we're pointing to 48. Where are we in 48? Well, we have already gone left, we've already printed, and now we just finished going right. So again, we're going to go up one more time. So we have just finished going through the whole left side of the tree, and now we're back at the root node at 55. So where are we with 55? Well, we just finished going left. So now we're going to print and go right. So we're going to start going right. Going right means we're going to go to 64. At 64, we are just entering 64 for the first time. So we are going to go left, which means we're going to go to 60. Again, we're just entering 60 for the first time. So we're going to go left, which is null. We'll come back up. We'll print. We're going to go right, come back up because it's null. And we will be at the end of 60's call. So we finished 60, so we're going to go back up to its parent, 64. Where are we in 64? Well, in 64, we have just gone left. Now we need to print. And we need to go right. It's just null. So it goes, it comes back, and it finishes the function for 64, which means it's going to go back to 55. So now it is in 55, it has finished left, it's finished printing, and it's finished right. And so that's the end of the function because it just finished the root node. So what do we see? Well, what we see is that we have printed out the nodes in order. So I'm going to leave this up on the slide so that the PDF of the slides has the right answer, and you can work through it on your own again if you'd like to. But this is called an in-order traversal of a binary search tree. So this pattern, going left, doing something, and then going right, recursively results in an in-order traversal of a binary search tree. There are three types of in-order traversals: pre-order, in-order, and post-order. And so we just went through what's called in-order. Being able to traverse a binary search tree in the order of the nodes is really useful. It's something that you might want to do for various algorithms that needs to look at them in order, or just to print it out. And the pattern is left, do something right. There are two other types of traversals, something called pre-order. Pre-order is going to go from the root node and traverse down. And then post-order is going to go from the leaf nodes and traverse up. They both have very different purposes. Pre-order traversal is really good if you need to make a copy of a tree, because you need to make sure that you're going through the tree in exactly the same order. As we talked about insert, we'll insert the nodes differently depending on the order that you insert them. So pre-order traversal is the only way to make sure that you have the same copy of a tree. Post-order traversal is what you'll want to use if you need to delete a tree, because you don't want to delete from the root down, because then you're getting rid of nodes that you need to then find the other nodes. So post-order traversal is really good for freeing the nodes. When you're working with trees, there's another thing to keep in mind, which is that there's different ways that you need to navigate through a tree. Sometimes you just need to traverse a single path. Examples of this are when you need to search for something, or insert something, or remove something. And in those cases, you just want to use a loop, because all you're doing is you're walking through the height of the tree, like for example to insert 44. The whole idea of the tree is that you don't want to traverse the whole thing when you're just looking for something, inserting something, or removing something. It's like the strength of the feature. So you wouldn't want to traverse the tree, you just want to traverse a single path. So you're just going to use a loop like we saw with insert and search. If you do need to traverse the entire tree, which you do in different cases. For one, if you want to see everything that's in the tree, if you want to make a copy of the tree, or if you want to delete the tree, you do have to go through every element of the tree. And these recursive traversals allow you to do that. So we did a in-order traversal, so now we are going to trace again with post-order traversal. Now again, like I said, this is a little bit painful to do, but after you do it a couple times, it's pretty quick. So we're going to do it again, but this time we're going to follow the post-order algorithm. Again, we're passing the root node in, so cur is going to be pointing to 55. And we're just going to read through the function. So the function says that we should go left, right, and then print. So we're going to go left first. So cur is going to point to... Okay, so cur is going to start with 55. when we recurse, we're going to go left, and then we're going to go left again to 47. Once we get to 47, you know that you're going to go left and return out because it's null, and then you're going to go right and return out because right is also null. So after you've gone left and right on 47, then you're going to print its value. Now we've finished the recursive call to 47, so we're going to back out and go up a recursive level to its parent, and so now you're at 48. So on 48, all you've done is gone left, so now you need to go right. So when you go right, you're going to go to 50. Once you get to 50, 50 is going to be a new recursive call, so you're going to go left on 50, which is a null pointer. So it's going to bring you right back out. Then you're going to go right on 50, which is going to take you to 54. 54 is a new recursive call. You're entering it for the first time. So you're going to go left, which is null, come back out. You're going to go right, which is null, come back out, and then you're going to print. So you'll notice how you're getting to the leaves first in this example. We went to 47, and now we've gone all the way down to the 54 leaf. And now we finished 54, we've printed it, so we're going to go up to its parent. Where are we in its parent? For this parent, we've just gone left, we've just gone right, and so now we're going to print. We're going to go up again to 48. Where are we with 48? Well, we just went left, we just went right, we're going to print. And now we're going to go to its parent, which is 55. Where are we with 55? With 55, we've just gone left. So now we're going to go right. We go right, we're in a whole new recursive call in 64, just entering it for the first time. So we need to go left. Okay, another new recursive call for 60. With 60, when we go left, we're going to get null and return back out. We're going to go right, we're going to get null and return back out. And then we're going to print 60 out. So we just finished our call to 60. So we're here at the bottom of the function call. So now we are going to go back up to its parent. Where are we with 64? So on 64, we've gone left. Now we need to go right. Going right is just null, right? There's nothing there. So it's going to go and come back quickly. And then we're going to print out 64. Once we've finished 64, we're going to go back out to the parent, which is 55, which is the root node. Where are we with the root node? Well, we went left, we went right, and now we're going to print. So this is what it looks like to do post-order traversal, and if you were paying attention as we were doing it, we were hitting all the leaves first and then we were going up their branches. So the answer that we got was 47, 54, 50, 48, 60, 64, and 55. So now we've done in-order traversal, we've done post-order traversal, and that's great, and these patterns are useful for these set types of algorithms. In order is if you need to go through the nodes in order for any reason. Post order is great for deleting the tree. And then as we talked about, pre-order is really good if you need to make a copy of the tree. But a lot of the times that you need to use one of these traversals, you'll have to decide which traversal is, most appropriate. So let's look at an example of that. Let's say that we wanted to tell if two trees were equal. So we would consider them equal if they have the same size, shape, and all the keys are the same. So these two trees are equal because that's true. These two trees are not equal because 5 and 3 don't match. And these trees aren't equal because this has an extra leaf that the other one doesn't have. So the question is, does it matter which traversal we use for equality? So take a second to just think about it before we move forward. Can we check the equality of the two trees using any of the traversals, or do we need to choose one of them? Okay, so the answer is that we need to do them in pre-order traversal. So in-order traversal won't work because there's lots of different ways that that you could make a tree and they're always going to be in order, right? That's the whole nature of a binary search tree. So the tree could be, inserted in all different ways, and it could have all sorts of different branches and values, but have the same in-order traversal. Post order is similar. You could have post order result in the same match, like they could have the same post order order, but the actual leaves are not in the same spot. So the only way to do it is, and it's the same reason that you have to use pre-order for the copy, is using pre-order traversal. So let's do that. So this is what the algorithm looks like. It's going to be a pre-order algorithm, but this is an example of pre-order traversal without it just being like printing it out, doing something else, checking if they're equal. So we're going to create a function called equal that will compare some other binary search tree object called other with the current object, which is pointed to by this. We're going to create a helper function that we send in the two different trees. So the helper function is just basically knowing that it has two nodes that it needs to compare. So how do we need to do this? So we have to think about base cases. So we're going to basically just continue to traverse the tree and continue to go left and right recursively. And so at some point, we need to get to the point where we are in a base that we know we're either true or false. So the first case is once you've reached a leaf, you know that if they're both reaching a leaf at the same time, then you are at an empty spot, and so they're going to be equal. Otherwise, one of them is and the other one isn't, and so in both of those cases, they're not equal. And so what do we do for the rest of the case? So for the rest of the case, we basically just need to make sure that the left nodes are the same, the values at the current nodes are the same, and the right nodes are the same. So we're going to check if all of those are true recursively, so it'll continue to waterfall down through the different nodes. And if that is the case, then we return true. Otherwise, it's false. And so this is a pre-order traversal because we're checking left, we're checking itself, and we're checking right, which if you go back to the pre-order traversal, that's the pattern of pre-order traversal. But you're seeing it in a slightly more complicated way where you actually have much more going on in the algorithm just other than printing it out because you're checking for equality. So these traversals can come in handy for all sorts of different algorithms with trees other than just simply traversing them to print them. So we've gone over all three forms of traversal, pre, post, and in order. And remember that there's two types of ways to go through a tree. One is to traverse all the nodes in the tree, which you want to avoid, and you only need to do in the cases that we've discussed if you need to walk through all of the nodes to compare equality, if you need to create a copy, if you need to delete it, or if you need to print it out. Otherwise, if you are simply using the tree to do search, insert, or remove, you're not going to traverse the tree, you're just going to walk down the path of the tree, the height of the tree, to find what you need. All right. That is it for BST traversals.